Hi everyone, I'm Imdi Nazmul. Today I'm going to discuss how we can utilize antennas in order to detect tumors in breast cells. The concept is very simple. Imagine if we place a breast tissue between two antennas, and these two antennas act as sensors. We can basically characterize any biological tissue in terms of electrical features such as permittivity and tangent loss. Basically, biological breast tissue is highly non-homogeneous material. It's a mixture of blood, fat, and many other biological components having different permittivity and tangent losses. But effectively and locally, we can model this entire breast tissue by using a single permittivity and tangent loss, which is basically a homogeneous modeling at a particular frequency. Due to the presence of the tumor cell, that homogeneity of the breast tissue will be hampered. And this change or this variation of the electrical material property of the breast tissue will be captured into the transmission coefficient or S21 plot. So the bottom line is the signal propagation from antenna 1 to antenna 2 will be impacted due to the presence of the tumor cell inside the breast tissue. Since this is a two-port network, we can definitely model this entire system by using a scattering matrix or S matrix. Because we have two ports, we'll have 4 elements in this S matrix, and we'll be concerned mostly with the transmission coefficient, which is basically S21 or S12 in this case. And if we plot the transmission coefficient versus frequency, then we might have different responses depending on the tumor size. Tumor location will also change the S21 plot. So by having these multiple simulation plots, we can establish a correlationship between the transmission coefficient with the tumor cell size and tumor cell location as well. So this is a very simple concept. By using 2 antennas, you can also employ multiple antennas around the breast cells in order to detect the tumor cell more precisely. And that could be done by using circular array of antennas as well. But for this discussion, I'm keeping it simple. I'm only designing 2 antennas and a breast phantom between them. Now, in order to define or in order to design this entire system in EM software or electromagnetic software, we definitely need electrical material property for the biological tissues. And this is our 3-layered breast tissue model or phantom. You can see there are different layers: skin, fat, and fibroglandular tissue, which is basically the dense tissues inside the breast. And it also determines the density of the breast tissues as well. And the tumor tissue is the big sphere in the center. And this is the table that I'm using to characterize this entire biological tissue in terms of its electromagnetic CAD model. Please remember that this is a single frequency data, so you cannot utilize this data for different frequency. And this is only valid for 33 GHz. And I took this data from a journal paper published in IEEE MTD journal or Microwave Theory and Technique journal. Now let's move on to the design part. I will design this entire project in CST from the very scratch. So let's move on to the CST interface. Once you open CST, you will have this template option. Go to microwaves and then antennas, and then planner, time domain. I'm designing this system for 33 GHz, so 32 to 34 will be a reasonable range. This is the graphical user interface of CST. Now let's go to modeling and then turn on the local coordinate system. Let's design the substrate first. Minus SL is the length of the substrate, and SW is the width of the substrate, and SH is the thickness of the substrate. I'm going to use Rogers 5880. is the substrate material. There you go, 5880. SL is 4.7 millimeter, SW is 4.7, and SH is 0.508 millimeter. Now let's create the ground plane, and since the current coordinate system is located on the top surface, we have to shift it on the bottom to create the ground plane on the back side, right? And before doing that, let's save the current coordinate system for later use. Patch center. Now let's transform the local coordinate system at the back side. Okay. And let's name it ground CS. This is our ground plane. U minimum is SL by 2. SL by 2. SW by 2. SW by 2. And this is the metal layer thickness, MT. Since this is a metal, we have to use PEC, or perfect electric conductor. 0.035 millimeter is the thickness of the metal layer. Okay, so this is our ground plane. Now let's come back to the top surface again. Just double click on it. And let's create the patch. This would be our patch 1. PL is the length of the patch. PW is the width of the patch. And MT is the thickness of the metal layer. PL is 2.75, PW is 3.1. Now let's create the microstrip line. So this is our microstrip. U minimum is 0. U maximum is the length of the microstrip, which is SL by 2 minus PL by 2. V minimum is the half of the width of the microstrip line. And this is another half of the width of the microstrip line. And W max is the metal thickness. The width of the microstrip line is 0.2. All right. Now let's create the inset. Okay. The insets are necessary to impedance to do the impedance matching to the microstrip line to the patch. So this should be W by 2. Inset 1, U minimum is the length of the inset. So INL, U maximum is 0, V minimum is 0, and V maximum is the width of the inset. And the W max is the same thickness of the metal layer, MT. Let's select vacuum as the material property. INL is 0.2 and INW is 0.15. We have to select this cutaway highlighted shape. Then an empty space will be created. In the same manner, we can create another inset on this side as well. It should be along V axis. All right. So MW, yep. this time inset 2. So this time U minimum is again the length of the inset, and U maximum is 0. V minimum is the width of the inset. V maximum is 0. Empty vacuum cutaway highlighted shape. Got it. Now we have to define the port. For that, go to Pix and then select this face, go to Simulation, Waveguide port. 1.5, 1.5, so you can see in real time the preview of the port. And this would be SH. Empty because it needs to cover both the thickness of the substrate and the metal thickness of the ground plane on the bottom side. That's why we have to add them together. Okay, and on the top side, you can just take the 1.5 times of the substrate height. You can see the preview, the outline of the port. Looks good. Okay, now we just completed our first antenna. We can just simply design the same antenna, or we can easily copy and paste it as the second antenna as well. That's what we will do now. Just let me turn on this working plane and let me increase the accuracy of the shape. Okay. Now let's go back to the patch center. Let's assume the distance between the two antenna is denoted by a single parameter called distance. So let me define the parameter distance, and I'm going to move it on the center between these two antenna, basically. So the distance between the two antenna is assumed to be 12 millimeter. Okay, and we can save this as the center of the system. Center system. And then you have to copy all the solids or the components that you created for the first antenna and transform it, and then just go to mirror and make sure you copy it. Okay, and you can see the preview. We just created another second antenna from the first antenna by taking this mirror function. Okay, great. So these are the second antenna's components. You can rename it. From the keyboard, you can use shortcut F2 to rename it. So this is our second antenna, right? This is 2, and this was for the first one. So let me define it as 1. This is for the second one, patch 2. This is for the second one, substrate 2. All right. So for the second antenna, we also need to define the port as well, like we did for the first antenna. So select this face, go to simulation and then waveguide port. This time 1.5, 1.5, and then this time 1.5 sh. And on the bottom side, you have to add the thickness of the substrate plus the thickness of the ground plane together. Got it. Now we have to define the abreast phantom between these two antenna. All right. Now coming back to the original coordinate system of the first antenna, patch center, just double click on this coordinate system, and it will be returned to this coordinate system. All right. Go to transform again, breast offset is 1 millimeter. And it's to the current coordinate system as breast base CS. All right. So this would be our breast tissue, the breast skin layer, and the radius is defined by a parameter breast red, and we will use the same value in the bottom radius and make sure the center are 0, 0, 0, 0. All right. Because we also need to define a new material for the breast skin, because remember in the first section of the presentation we showed a table and we showed that at 33 gigahertz of frequency we have to define this entire biological tissue in terms of permittivity and tangent loss. So that's what we are doing now. We are going to define a new material, breast skin. Let's change the color. The tangent loss of the breast skin was 0.93 and the permittivity was 17.7. Sorry, 17.7. And the tangent loss was defined at 33 gigahertz, right? So you have to make sure that you enter this frequency right in this box. And you will see some graph, CST's built-in graph for the material characterization. But anyway, you can continue from this dialog. If you press OK, then it will ask for the breast radius dimension, which is basically 10 millimeter. And then you will see that the component has been created. All right. Now, we need to define the second layer, which is basically the fat. Remember, our breast phantom was a 3-layer tissue. On top of the layer, we had that skin layer, and the second layer was the fat, and the third layer was fibroglandular tissue, right? So let's create the fat layer now. So this is going to be breast fat. And the center radius is breast rad minus 0.5. So this 0.5 millimeter offset is because of the thickness of the skin layer. And make sure your bottom radius is equal to the center radius. And the center should be 0, 0, 0, 0. You have to define a new material for the fat tissue. You can name it breast fat. And change the color as well. The permittivity for the fat layer was 3.4. And the tangent delta, which is tangent loss, was for the fat tissue 0.16 at 33 gigahertz. Okay. And you have to select this again. Insert highlighted shape. Once you do that, you can check in the component section that your fat layer has been inserted into the skin layer. So this is your skin layer, this is your fat layer. And the third layer, which we are going to create now, will be the fibroglandular layer. So this is our third layer. Breast fibro. This time, use 1 millimeter as the offset because the thickness of the skin layer is 0.5 and the thickness of the fat layer is 0.5. So that these two add up to 1 millimeter. Use the center as 0, 0, 0, 0. And again, we have to define a new material for the fibro-glandular tissue, fibro, let's say breast fibro. The permittivity for this tissue was 16. Let's change the color. And the tangent loss was 0.94 at 33 gigahertz. And then again use this insert highlighted shape. And then you will have this 3-layer breast phantom model. All right. So this is our skin layer, this is our fat layer, and this is our third layer, fibro layer. Okay, now we have to do a little bit of work. Local coordinate system. Let's move on. This is areola. Distance. So this is our areola section. Center radius is areola, red, and the bottom radius is same. Center should be 0, 0, 0, 0. And you can use breast skin as the areola section. Let's use 1 millimeter for the areola. And again, you can use this insert highlighted shape. Okay, now we have to design the tumor cell inside this, somewhere inside this breast tissue. All right. In order to do that, go back to the original patch center coordinate system, and then we are going to localize, or we are going to parameterize the location of the tumor tissue in terms of variables, so that if we just enter the variables, or if we want to modify it later, we can just do it in the parameter list window. So for that, we need to define 3 new parameters for the location of the tumor cell. Let's define as Tx, the coordinate, the x coordinate of the tumor cell, Ty, the y coordinate of the tumor cell, and Tz as the z coordinate of the tumor cell. For the initial value, let's use 0, y coordinate 0, and z coordinate, let's use 5. So this is right inside of the breast. We will create a tumor cell. This is the tumor cell. You can name it tumor. Tumor radius. We have to create a new material for the tumor cell. And the permittivity for the tumor cell was 18. And color, let's select black. And the tangent loss was 1.05 at 33 gigahertz. So The radius of the tumor cell, you can change it later, no problem. For the time being, 2 mm is fine. And again, use this insert highlighted shape. And then you will see the tumor cell is located inside somewhere of this breast tissue, right? And you can easily change the location of this tumor cell by changing these three parameters, Tx, Ty, and Tz. For example, if you want to change the location of the tumor cell on the x-axis, just simply change it and press F7. And you'll see it moves. It moves automatically. It is very useful to parameterize the location. Again, see? So this is the advantage of using parameterization of the location for the tumor cell. So for the time being, let's keep the tumor cell in the center position. So this is our whole system design in CST. We have this breast tissue or breast phantom. Inside it, we have this tumor cell. And then we have these two antennas on the two sides. And then you can simulate it and find out the S21 response with respect to frequency. All right. Now for the simulation, go to Setup Solver. Normalize to fixed impedance 50 ohm. You can enable this adaptive mesh refinement, but it will take a lot of time because it takes the system's memory and processing power to optimize the mesh in each passes. If you have a limited resources, like you are simulating it in your laptop, maybe it will be good for you for the first time not to enable it, but definitely for accurate result, you eventually need to enable this option, adaptive mesh refinement, in your simulation. And yes, you can control it here. You can change this value, create a little bit flexibility in your system. For example, if you make it smaller, it will take more time. The results will be accurate, but it will take more time and resource as well. But if you make it bigger, then the resource will be used less and the time will be reduced as well. Also, you can increase and decrease the number of passes for which it will check the S parameter value. This delta, maximum delta, is the error function of the S parameter value. And this will be continued for these 6 passes. So if you want to reduce your time, you can also reduce this number like 4 or even 3, or even confine it to 2 and 1 as well. 1 doesn't make sense, basically. At least you need to find out the error, right? Anyway, so 2 and 3 or 2 and 4 would be a good option for the limited resource users. Anyway, so you can also add parametric sweep in order to check how the S21 will vary if you change the location of the tumor cell and the size of the tumor cell as well. For example, you can add new sequence and then add a new parameter like the radius of the tumor from 2 mm to 5 mm, or let's say 1 to 5 mm. The radius will change to 1 to 5 will be a little bit bigger, maybe 3 is okay. And samples, maybe you need 6 samples. All right. So you will see that there are 6 tumor radius values that is going to be used for different simulations, and you will get a response of the S parameter in terms of this dimensional variation. Also, you can add another sequence for the location of the tumor cell, and add the parameters like Tx, let's say from 0 to 5 with the samples of 5, and another parameter Ty from 0 to 5 with the samples of 5, and another parameter for the Z coordinate of the tumor location, TZ from 0 to 5, samples 5. But remember, the more sequence and the more parameters you are going to use, it will take a lot of time and your simulation will be elongated. So make sure you are using your resources in a proper way and you do not elongate your simulation unnecessarily. If you have a powerful system, you may try to find out this parametric variation and you can do it later, no problem. And then you can just press start to start the simulation. Once the simulation is complete, you can see the S21 plot from the 1D results, and you can go to S21 plot here. So for different tumor size and the locations, you will see the S21 plot is different. And like I showed before, you need to perform parametric sweep in order to produce more than one S21 plots for various cases. So I hope that this video has been very useful for you to know how to design this entire system in CST from the very scratch. And independently, you can design these tumor detection sensors by using these antennas in CST. So if you find this video useful, press like and subscribe to our YouTube channel. And if you have any question, you can join our Facebook group called Antenna Lab and post your question there. Thank you very much for watching this tutorial.